Right, well, I think we're going to get started then. So thank you everyone who's here so far, and we're going to get started with Modexoft's fifth now webinar outing. It has been a little while since our last one, but hopefully this will be of great interest to many of you that are here today. We're going to be talking around again various aspects of ElectricalOM later. But we're going to look at just quickly a little bit more around our compliance structure within ElectricalOM. So we've looked at some of these aspects previously in our other webinars, and today we're going to be focusing specifically on the Arc Flash and study system for ElectricalOM, and we're going to be talking around Arc Flash here today as well. We have a keynote presentation through a special speaker with Mike Frain, who's here with us today. He's going to be talking around the specifics of Arc Flash, particularly in Europe. And then the second part of our presentation will be undertaken by Dimitris, who will be showing ElectricalOM and the functionality we have there for calculating and providing information about Arc Flash as part of the system safety. As we go through the presentation, you have opportunity for asking questions, and we'll do a Q&A session at the end of Mike Frain's presentation. If you can, at the bottom of your screen, you should see a Q&A button there. So if you do want to have any questions asked or answered, if you can populate them in the Q&A there, we will cover them as best as we can during the presentation. Any questions that we don't get time to go through, we will get responses out to you after the presentation at some time later on. One of you who is attending today will be randomly selected to receive a copy of Mike's new book, European Arc Flash Guide. And anyone who decides to purchase the Arc Flash module for ElectricalOM will also receive a copy of that book as well in the future. After this presentation, excuse me. After this presentation, we will be doing other webinars coming up. In March, on March the 8th, we are doing a presentation with the ECA on a number of the new features and things that happened with ElectricalOM. So hopefully there'll be some of you that will be able to attend and join us for that information as well. That said, I'm going to hand you all over now to Mike Frain, who's going to provide his keynote on Arc Flash. Thank you.
Well, good afternoon, everyone. I noticed one or two people from elsewhere in the world, so good morning and good evening as well to you too. So my name's Mike Frain, if you've missed the introduction from Spencer. Thanks to Dimitris for inviting me along, and to Spencer for hosting today. It's my pleasure to speak to you about the Arc Flash hazard and the available methods and means for risk management. Firstly, I'll run through my credentials, which starts with many years of practical application across Europe and beyond. Working in most industries, one or two industries I've not worked in so far. I've not worked on an oil rig yet, but I'll leave that on my bucket list. Many of the industries that I refer to are blue chip household names. So just to run through one or two things about myself. Okay. I'm the Vice Chair for the IET Safety Policy Panel and head up the IET Arc Flash Working Group. And they were responsible for the new Arc Flash Risk Management fact file that was recently written and published. So I'll say a little bit about that later. I'm an expert for the British Standards Institute, Live Working Technical Committee, TC78, and appointed expert for the IEC. And on the IEC, I'm the convener for the IEC Arc Flash Working Group 15, and also the project team leader for the IEC Arc Flash Guidance for End Users projects. And finally, I've been privileged to work with an abundance of household names in most industries, and I suppose more than that, I've been fortunate to have worked alongside people who have contributed so much to electrical safety around the globe. And indeed, I've made long-lasting and enduring friendships along the way. so blessed in that way. So today, I'm going to describe new resources about the subject of arc flash hazard, including my new book, and hopefully there'll be somebody walking away with a copy of it, and also if you're purchasing the ElectricalOM software, you'll get a copy of the guide as well. The resources enable risk management for educational purposes at one extreme, and right through to a one-stop shop for those who have responsibility to design power systems or to put people to work on or near energized electrical equipment. As you can see here, I've ordered the resources into 3 categories. Firstly is the strategy or what you should do. Secondly, the how to do it. And thirdly, the means to carry it out using simple and easily accessible tools and calculators, and also the ElectricalOM module. Before that, there's always some people on these events that perhaps the subject is new to them. So let me explain what arc flash is and how it manifests itself. And the next few slides will do that. This low voltage model is one that I've used many times on training courses to explain the phenomena to delegates at even seminars and training sessions and so on. Arc flash is usually caused by inadvertent contact between an energized conductor, such as a buzz bar or cable, with another conductor on Earth's surface. Put simply, it's insulation breakdown, and very often the insulation in question on low voltage systems is simply air. Sadly, the cause of insulation breakdown is, I'm afraid to say, very often human intervention. If you can see in this diagram, there are 2 copper buzz bars that are facing each other by a 30mm air gap, and then it's connected to a 400-volt electrical source with a prospective short circuit capacity of 25,000 amps. I suppose it's the sort of output that you get from a 1000 kVA transformer, which tends to be pretty ubiquitous in industry nowadays. As you can see, there's no protective device in circuit, there's only a switch. There's a piece of fuse wire which is connecting the 2 buzz bars together between that 30mm air gap. When I ask electrical workers a question, what will happen when the switch is closed, they often say that a large amount of current will flow and then the fuse wire will simply rupture or blow and rapidly disconnect the circuit. Well, actually what happens is that the fuse wire will vaporize, it'll melt, but in doing so will ionize the air between the 2 conductors and create a low impedance path. Large amounts of current will flow, creating temperatures as high as 20,000 degrees centigrade at the seat of the arc, which will immediately vaporize any element known to man. There'll be a massive expansion of air and vaporized conductor material, which causes an electrical explosion. The thermal effects can cause horrific burns and ultraviolet radiation, which can cause arc iron, ballistic effects, which can cause blunt force trauma to anybody stood close by. The consequences of electrical arc flash are not just personal injury, but they're wide ranging. I give examples of each of these in my book from my experiences. Just recently, an electrical contractor was fined £1 million in the UK, plus costs for breaches of Section 2(1) of the Health and Safety at Work Act 1974. This was following burns to an electrician whilst he was undertaking routine testing. That was on a low voltage system. In the UK, theoretically, it doesn't need to be a personal injury. And actually, it comes out of a requirement to report an arc flash event under the UK Reported of Injuries, Disease and Dangerous Occurrences regulations, that's RIDO. And then there's the other losses like damaged brand, severe equipment damage, lost production, environmental damage. I'll give examples of each of those in the book. Realise limited time today, so I'll skip on from that. Well, what are the legislative responsibilities? Well, arc flash is just another hazard within Europe anyway. It can't be ignored in the same way as any other hazard can't be ignored. And that's because of the EU Workplace Health and Safety Directive 89391. It's commonly known as the Framework Directive. And anyone that's in the UK, that's mirrored in member states as well as the UK post-Brexit. So there's a requirement in both pieces of legislation for suitable and sufficient risk assessment. And then mentioned in there as the principles of prevention. There are actually 9 of them. I'm just mentioning 3 there, which is the avoidance of risk, the evaluating of risk that can't be avoided, combating the risk at source, and so on. There are actually 9 principles of prevention, and because of principle of prevention, PP is not mentioned in any of them, by the way. But getting rid of the risk, perhaps dead working, something like that, evaluating the risk which can't be avoided, and that's where you need to be able to calculate the risk in the ways that I'll be described later on. So this brings us to the first element of the new resources that I mentioned earlier, which deals with strategy. So the IET fact file, which deals with strategy at a higher level, I'll talk about in a little bit more detail, but within the European Arc Flash Guide, the book, there's a lot more in-depth information in there. So the following is a brief description of the approach, the fundamentals of risk assessment as applied to Arc Flash. You can see there's 3 principles of Arc Flash risk management. The first one's highlighted, and the second 2 are greyed out there. So at a basic level, we're asked to consider the 3 actions shown here. We're asked firstly to identify what could cause injury, and in other words, hazards. When we look at arc flash, it's derived from system parameters such as voltage, such as fault level, and electrical protection arrangements. And secondly, in our very simple list is we have to consider how likely it is that somebody could be harmed and how seriously. In other words, this is what the risk is, isn't it? For arc flash, it's derived from system conditions, such as the condition of the equipment, the quality of the installation, measures used to contain an arc during switching under normal or fault conditions, how well it's been maintained, and whether it's been operated in accordance with its original design. But very importantly, it's also directly related to the task to be performed and whether you should be there in the first place. And then finally, we need to take action to eliminate a hazard, or if it isn't possible, control the risk. And we do this by applying the 4P approach to eliminate or control the risk. I created the 4P approach back in 2008, I think it was, and it's stood the test of time. There's various organisations still use it today, and I've tweaked it a little bit over the years, but this is the 4Ps shown there, which I'll describe in further detail very shortly. It's a predict, prevent, process, and protect. So then this brings me on to how, which is described in much detail in my book, the European Arc Flash Guide, but it's going to be summarised very briefly today. Firstly, about the book, it was published in autumn of last year, and it's done extremely well. The feedback that I've had is mind-blowing, to be quite honest. I've received it from peers and leaders in industry around the globe, and it's been overwhelming. So I can see some of the comments that I've had or received or shared on platforms such as LinkedIn. Very happy to receive some of the comments that I've had back on that. So I'm grateful to all those that have taken time to give us some feedback and make my endeavours all worthwhile. So the first part of the book deals with the 4 Ps, and it seems that the 4 Ps are talked about again by various organisations nowadays as a means to manage the arc flash risk, but it could be applied to any hazard actually. So the first part deals with the 4 Ps, and this cycle diagram here, it illustrates a concept approach. If we start here with the red segment, predict, we look to calculate and validate, using the calculators and tools that I mentioned earlier, as well as the ElectricalOM software arc flash module. So the first thing that we'll do is to predict the severity within the predict section in red there. Once we've done that, we'll obtain results, and from those results we then move across into the prevent section, where we start to think about if we've got high levels of hazard, incident energy, as we'll talk about in a little while. What are the risk reduction measures that we need to take? And that's done through a hierarchy of risk controls. As you can see here in this decision box, can we apply further prevention techniques? And I'll talk about some of those prevention techniques as much as I've got time for today. So if we can, we go back again, we reevaluate, we predict the severity, and once we've done that, if we've exhausted the prevent section, because that's the first line of defense, in there, as you'll see, is actually switching the power off, but other things as well. And if we finish at that point, then we go into the process section, which is all about policies, rules and procedures. And we'll talk about safe people, safe procedures and safe places. It's all about competence, having equipment that's properly maintained and so on, and same with the place of work. And then finally, once we've exhausted all that, if there is a residual risk, then we apply the protection measures through PPE. And hopefully by that time, we've been able to reduce the risk, and any PPE that we do have to provide is going to be of optimum solutions. In other words, it's not going to be as expensive, and it's not going to create a problem for the user in terms of being very heavy. So let's go back to the predict section. If you look in the top right hand corner, here's our little cycle matrix presented a little bit differently. So the other boxes are grayed out. So we're looking at the predict area here, and we'll start with here. And as the saying goes, by Peter Drucker, I think, who invented it, you can't manage what you can't measure. So in other words, if you're able to measure the level of hazard, then you can start thinking about how you manage it through risk controls. The IEEE 1584 guide shown here on the right-hand side is a guide for performing arc flash calculations, and it's the most comprehensive means to evaluate the arc flash hazard, and it's an internationally recognised and auditable standard. But there are other methods described in the guide and later in the presentation, and I'll talk about those and how you can get those in the methods as well. Firstly, the IEEE guide, if we just go down the list on the left-hand side, it allows you to calculate the arcing current, which is very important if you wish to design out the hazard on electrical equipment. Now, right at the end of this presentation today, I've put a special slide in for all you design engineers out there, because I'm going to just talk a little while about designing around arcing current. So if you forget everything else that I'm going to talk about today, arcing current is quite important, because that's what your protection has got to protect against if it's going to quickly disconnect an arcing fault. And I'll share that with you later. So on the second point, it calculates the incident energy, which defines the severity of the arc flash at a certain distance. The true SI unit is joules per square centimetre, although it's popularly expressed in calories per square centimetre. 1.2 calories then per square centimetre, or the true SI unit, 5 joules per square centimetre applied to the skin for 1 second is a threshold at which there could be an onset of a 2nd degree burn. And this figure then is used in determining the PPE requirements and the arc flash boundary, which I'll mention as well. So lastly, an arc flash boundary can be calculated. It's where the incident energy is reduced to its key number of 1.2 calories per square centimetre. So again, I'll mention that again. Might just be clear that the guide, the IEEE guide for 1584, the recommendations for PP are excluded. This is all about hazard. What you do about it is outside the scope of IEEE 1584. So what affects arc flash severity? Well, there are 2 things initially. So if we're looking at this network here, feeding a low voltage control panel, the first thing that affects arc flash severity is the arcing current, and that's determined by the fault current upstream and the voltage and so on to provide the arcing current. And as I mentioned incident energy earlier, there's a direct relationship between arcing current and the amount of incident energy that's derived from an arc as a result. And the other thing is time. So how quickly you can disconnect an arcing fault determines the amount of damage that's going to be done to your equipment for a start, but also to those nearby as well. And again, that's a direct relationship between time and the amount of incident energy. So if you've got a disconnection time of, I don't know, 100 milliseconds, if you can cut it down to 50 milliseconds, you will halve the amount of incident energy. The other thing that affects severity, I might just mention there are other things that I'm not going to talk about today, such as motor contribution and things like that, you know, so forgive me on that one. But the other points that affect severity is the distance from the arc source, and it's an inverse exponential relationship. In other words, small increases in distance can drastically reduce the energy level. And the intensity of an electric arc and the resultant level of incident energy is then affected by the electrode configuration. You can see on the right-hand side, I've just put one of the 5 electrode configurations, which is arc in a box, basically. That's VCB, vertical conductors in a box. So the other issues that affect the arcing current and the incident energy is horizontal conductors versus vertical ones, open air versus enclosed, the size of the enclosure, how the conductors terminate, and also the gap between the conductors themselves. Quickly, then, the incident energy exposure level is measured to the person stood in front of a perspective arc, to his face and his torso, depends on the equipment type, and also that working distance from the arcing source, which alters depending on what you're actually doing to the equipment itself. The other thing is arc flash boundary, that promise I'd come back to. So the arc flash boundary, it's a distance from the perspective arc source at which the incident energy level is calculated to be 5 joules per square centimetre or 1.2 calories per square centimetre. And it's the onset of the second degree burn, which is used to determine that. So the next part is the prevent section. If you look in the top right hand corner, you can see we're now on the green segment, which is prevent. And I'm not going to talk in detail today. I'm just going to deal with a couple of these, but I'll go through them anyway. And there's lots and lots of information in my book, you know, about risk reduction measures, and you know, you'll be able to find more information there. So prevent must be the focus of attention when managing the risk of harm from arc flash. And this table categorises those risk reduction measures into dead working, which must be the principal prevention measures. And then the second one in orange there is automatic disconnection of supply, ADS, which is the detection of dangerous arcing current, then the automatic disconnection of supply. The third category is equipment design. And then finally, operational measures. And all these measures are described, as I said, in my book. And also there's a presentation video on the subject. If you want to drop me a line, I'll be more than happy to share some links to show further videos that give a bit more information in there. Do that with pleasure. I'm going to talk about the first two items, the elimination of live working, adjusting protection settings, and also arc flash maintenance settings. The reason I'm going to talk about arc flash maintenance settings because Modexsoft have just announced that they've got it within the arc flash module, the maintenance settings as well in there. So I'll talk about that. And the others I won't have time to go through today, but improved protection settings, arc detection, all come under automatic disconnection of supply of arc detection with picking up the light that's emitted from an arc internally in switchgear, and then we're looking at the rising current and then disconnecting very quickly. Equipment design follows on from that. The active internal arc suppression does everything arc detection does, but it also clamps a short circuit across the bus bars and sometimes to earth as well. You know, and the very quick acting, you know, we're talking about 4 milliseconds from the initial arc itself. Improves forms of separation in PSC assemblies, arc protected equipment, improve racking design as well. And then operational measures, a holistic approach to system design, installation and maintenance, which I go into in some detail in the book. Operation sequence alterations, you know, like paralleling transformers and things like that. Remote operation, I mentioned about the distance and incident energy, and the more distance that you can put between you and a prospective arcing source, there is a massive reduction in incident energy. And then non-intrusive diagnostics as well, that's still within that point. So I did say I mentioned dead working because this should be the first port of call for anybody that's wanted to reduce the arc flash risk. And in this case, testing for dead still carries risk, I'm afraid. It needs a high level of risk assessment. You know, for instance, if you've got safety considerations for an individual making safe for an underground high voltage cable, for instance, it's going to be of a much higher order than that's for somebody just isolating a piece of equipment for local isolation point for themselves. So, you know, there has to be a high degree of knowledge and so on, i.e. competence. Next is about equipment design. One of the points I'd made was try and design out the risks so people aren't testing on live equipment. That segregation of power and control, safe control systems, protection by barriers and built-in test points. And finally, treat all electrical equipment as live until proven dead. And I describe in my book about one particular individual who actually tested on what he thought was dead equipment. It was a cable which was live, which had been hit by a digger. And when he went down to test it, of course, it flashed over in his face. But it didn't happen just once. That same individual did exactly the same thing some years later, and in that case I don't think he returned to work. The next thing is what I call the low-hanging fruit of arc flash management, and that is looking at protection coordination and protection settings. And from my experience, by moving the instantaneous setting, if we've got there, for instance, we've got 4,300 amps, which is taking a second to actually clear. If we're able to move the instantaneous setting, that same 4,300 amps may look more like 0.02 seconds. So that happens to account for probably 90% of actions to prevent injury and damage. And on the same theme, ADS, maintenance protection settings, we know that if we could reduce the settings for the duration of the work, even if that upsets coordination, if it's just for the duration of work. But there has to be care required to control that activity. But the point is, manufacturers are now providing protection maintenance systems, such as Eaton here. They recently patented a system that they call arc flash reduction maintenance system, ARMS technology, for low voltage molded case and air circuit breakers. And it allows for a maintenance mode to be set on a circuit breaker, which it'll in effect provide a lower instantaneous pickup level via a separate maintenance setting. And when fitted, it operates independently of the main protection. So you can see in this particular case, I don't know if you can see my mouse in blue there, that's the normal setting, and the maintenance setting is in red. So in reducing the amount of time to disconnect a fault, it'll reduce the incident energy as I've described earlier. And very quickly, I'm going to go to process, big section in the book, which is all about safe systems of work and about information and training. And I'm not going to be able to cover that today. It's such a big topic, but I do like this diagram, which speaks about the electrical safety management system, which encompasses safe people, safe places, and safe procedures. So for safe people, we're talking about competence, about providing information, training and instruction, about supervision and control. Safe places talks about well-designed and documented installations, maintenance and confidence in protection systems, and safe procedures about risk assessment processes and specific rules, clear responsibility and authorizations for work. And then finally, we're into protect, and this is where this is the last protocol. If you look at the hierarchy of risk control measures, we started at the top with sorry, I'll go back on that, a bit trigger happy. Elimination of a fault hazard, making things dead in the first place. Personal protective equipment is what you do when all else has failed. And within Europe, there's a European Council Directive 89656 EC, use of protective equipment. Bear in mind, though, that arcing faults in oil-filled equipment, PPE won't protect you against that. And in fact, I've got knowledge of people who have been killed as a result of that many years ago in my case, but the memories still are foremost in my mind. PPE won't protect you against that, I'm afraid, about disruptive failure of oil-filled equipment. There are differences in Europe, ELA box tested PPE, which again is for another day. And then there's a diagram that I used to display what you should be doing when you're looking to protect against residual risk. Firstly, analysis and assessment of the risk. That's box A there, through the 4 Ps. And then define the PPE characteristics and always take into account environmental conditions and other risk. And there's a form within the book which you can use to do that, actually. In box C, compare the PPE characteristics in B with availability. And so you won't get what you're looking for, I'm afraid, straight away, because the market availability won't allow you to do that. It's got to be a trade-off and looking for the best fit generally. And then from there, choose PPE. A lot more I could say about that. So I didn't think that providing the knowledge to deal with the strategy and how to do it would be enough. If this is what I'm trying to do. So I teamed up with a very clever computer scientist, and we were able to provide the means in order to put together simple and accessible tools. So it gives you the means to do everything that we've looked at within the strategy and the how to do it. And that's all on www.ea-guide.com, and there's a video on the first page which tells you all about it. It only takes about 5 minutes, I think, to run the video. Just tells you a little bit more about it, much more than I've got time for today. But the calculator structure, what you'll find in there, if you look at the arrow on the left-hand side, A, we've got 4 calculators there that are based on the IEEE 1584 2018 calculations that I talked about earlier. There's the IEEE 1584 calculator. There's also an easy to use low voltage circuit breaker calculator, which lists out most of the devices within Europe. Then there's the IEC HRC fuse charts, what we've provided in there, and also for devices below 125 amps. And then in B, arrow B, we've got theoretical papers, and there's a calculator there for calculating the instant energy for DC, and also blast pressure. Within C, there's the German algorithm, which is based upon the box test. It's an IEC box test within Europe, which is the DGUV standard. And there's a calculator in there to provide support for that. And then to support all the other calculators, the prospective short circuit fault current calculator. There's a tool for looking at the HRC time current curve, and also IDMT tool as well. So nearly there, and I've finished. But before I do, I realise that there's a good number of you that are responsible for low voltage system design. So I'd like to dedicate this slide to you. So if incident energy and arc flash boundaries and so on are a little bit of a yawn to you, I think the calculations just providing information on the value of arcing current is really valuable. It's not, well, I hope it wouldn't become as much of a surprise to find that the arcing current will be lower than the available prospective short circuit current because of the impedance in the arc. At high voltage, the attenuation is very much less than at low voltage. And you can see in the graph here, it shows that the arcing current against prospective short circuit current for 3 different electrode configurations. Firstly, for a 10 kV system, popular in Europe, 11 kV generally seems to be the distribution voltage in the UK, and 400 volt system voltages, which is harmonized across Europe. Whilst you're extremely unlikely to experience fault levels at 50,000 amps on 10 kV or 11 kV systems, it just serves to make a comparison, I think. So to know the level of fault current that can flow in and out is for me essential information to you as a designer who wishes to know if your electrical systems are going to clear an arc fault quickly, and it's going to clear safely, and it's going to be with minimal damage. Or, as a good friend of mine always says, is it going to disconnect very quickly, or is it going to be sometime next Tuesday? And that's when your real damage starts. Remember that we've got a direct comparison between time and incident energy. So what this graph also says is that overcurrent protection clears dangerous arcing faults. And after all, most calculations are based upon prospective fault current only, and automatic disconnection times for shock protection only. So as you can see at 400 volts there again on the graph, that difference between the fault current and the arcing current can be quite marked. If we're looking at 50,000 amps prospective short circuit current, the actual arcing current could be as low as about 26,000 amps. And if your protection doesn't see that as a short circuit or just sees it as an overload, that's when you can get to extreme amounts of damage. So thanks very much for inviting me along again, and thank you for listening. If there are any questions, I'll take them at any time, now or towards the end of the other presentations.
Okay, so I think we've just got one question that's popped up at the moment. So if anyone has got any more questions, please feel free to populate some in the Q&A there. But the first question that we've got come in here is from Paul, and he's requested, as much as the arc flash research and the IEEE standard is based on US switchgear and practices, how does this directly correlate to the different construction of switchgear in the IEC world and the different more stringent standards, such as not just the IEC BSCN standards, but the LDV, which requires safe design, which should fundamentally minimize the risk of arc flash by law, not just by product standard, which should reduce the risk lower than the minimum legal requirements. So just sort of, I'm assuming there in sort of short term is, obviously early on in the slides, you referred to the IEEE standards as part of what you were looking at in terms of risk safety management there around arc flash incidents. Do you think there's a real relevance in Europe for the IEEE standard, or do you believe that it is more of an American-based standard for that sort of market?
Well, I wish it was, to be honest. I've probably trudged around more industrial facilities, power stations, utilities, and as many manufacturing facilities that you can name. And I wish that was true, you know, when it comes to what actually happens within the marketplace itself. I do talk about the design from an IEC design perspective within prevention. I haven't been able to talk about it in detail today. I think it was Paul, wasn't it, that I'm addressing. So Paul, I do deal with all that within the book on an IEC, which is a global standard, obviously, but very much around what I see in Europe. The IEEE standard is based on 60 hertz and 50 hertz. It's been validated for both. In terms of the equipment that it's looking at, there's no physical differences that I can name between what happens in the US and what happens in Europe. There aren't any. You're quite right to point out that the stringencies of our standards do tend to be higher for new equipment. But I'm afraid to say at low voltage, those standards can be very quickly dilapidated from people actually working on the equipment itself. I've got so many galleries of horrors that I've seen where essential safety equipment's been removed off switchgear and so on, and people work on the equipment itself. As I mentioned earlier, it's all about the task. What are you doing there in the first place? And there'd be no need for all this, I don't think, if people actually, worked on equipment in a proper manner and maintained it in a proper manner. And notwithstanding that, I deal with sites where you've got equipment which is, believe it or not, 50 or 60 years old, and that was manufactured to a far different standard back then. Some would argue, by the way, that it was, copper bottom standard, cast iron and things like that. But I'm afraid sometimes the instant energy calculating the amount of hazard within the switchgear itself, points towards what could happen. And if the equipment is dilapidated, if there's been ingress of moisture or dust or vermin or whatever it might be, the second part of the questions that I put forward earlier about the risk, in other words, we talked about hazard, just how big is the bang going to be? Is it going to be a pussycat inside that switchgear, or is it going to be a tiger? The second part is the risk. And the risk is all about what you're doing there, is about whether it's been maintained properly and all those other things that I mentioned there. So I wish I could put my hand on heart and say to my colleagues in the US, we've got it all sussed over here because all our equipment is fine and dandy, to using their terminology, and we don't have to do this sort of thing.
Okay, just a couple of items just popped up there. I think Paul's just popped up with another item there.
Yeah.
So are we admitting that the manufacturers are supplying illegal switchgear and employers are not supported, or employers supporting illegal operating practices, noting that the first LVD was implemented in the UK in 1975 under the Health and Safety and Work Act, and in 1974 and the EAWR in 1989. I'm not entirely sure how we would answer that one. Is that something you would like to tackle, Michael, or should we maybe just...
No, I'm quite happy to deal with that, Paul. I think everything that you say is absolutely correct. And it's not a case of admitting anything. The fact is that if you've got equipment which is high hazard, there's a lot of equipment which is high hazard, not just arc flash equipment. It's whether it's contained. And in terms of the thoughts that I put forward earlier on there, yes, even down to doing the arc flash calculations themselves. I looked at IEEE 1584, the 2002 format, and in the back of that booklet there was a section, Appendix A, which talked about the amount of effort it was needed to do an arc flash study. Now, I can't remember the mix entirely, but it was split down into a single line diagram. That's the first thing that you need. The second thing that you need is a fault study. The third thing that you need is a coordination study. Now, unless I'm missing something, as I actually presented many years ago, I think that any electrical engineer in charge of an electrical system within the UK, worth the salt, would need those three items in place, wouldn't they? You know, so single line diagram, surely to goodness, you know, if you're a duty holder, you ought to have one. Secondly, you should know what your fault levels are. The third one is, surely to goodness, you know, you've looked at protection coordination. But if I told you that the amount of effort that was required from Appendix A of the 2002 model of IEEE 1584, the amount of effort for doing the arc flash part of it was only 9%. Only 9%, so it's less than 10%. So I think in not knowing what the incident energy levels are on a complex electrical system, it's not too much to ask if you should be doing the first three. And as I recall, I was told that expect people to have those things in place would be utopia, and I'm afraid I don't agree with that at all. So thanks for your question on that, Paul. Thank you.
There was a bit more clarification there, but I think we'll probably finish that off later on. There was just one other question from Don, who is saying, not dismantling and abusing equipment is not mitigated by the calculation of energy. Does not dismantling and abuse only likely to make any calculation invalid?
I'd say just say that again.
So it's referring to obviously when calculations are being done as part of checking your arc flash, and it's querying if the system is being dismantled and abused, is that not only likely going to make any calculation done as part of design invalid?
Yeah, I'd agree entirely with that. You know, if people are doing things on electrical equipment that's not designed to do, or shouldn't in any case be in the procedures, and the thing that I have been doing for this past 20 years and beyond before then is writing safety rules and procedures for large companies. Arc flash is part of that. A small part, I've got to say, is you don't allow people to indulge in unsafe practices wherever it is, and you know, make sure that what practices they are allowed to do is that they're actually authorized in writing to do it, and that they're competent to do it.
Yeah, so again, we're looking at that hierarchy of prevention and the hierarchy of safety within your system.
Yeah.
Okay, well, thank you very much, Mike. I think that's all for the questions for now. So we're going to move on now into the next section. So Demetrius is going to be sharing up and showing some of the things that we're doing within the ElectricalOM software in and around arc flash calculations, and how we're doing some modeling in and around those systems as well. So if Demetrius, if you would.
Hello. Thank you, Michael. Thank you, Spencer, and definitely nice and informative presentation from Michael. Giving us all this knowledge is invaluable. Thank you, everybody, for joining as well. I hope you find this webinar informative and something that will help you on your practice, especially when you deal with arc flash assessments. As Mike already mentioned, it's very, very important in order to calculate the arc flash study energies and you know, the PPE categories to have in place the single line diagram with all the information required to calculate the fault levels, and of course define the necessary devices which will eventually conclude to the disconnection times based on the fault levels. And based on all these figures, we will be able to calculate the arc flash incident energies. All right, so here I have an example in ElectricalOM that demonstrates a single line diagram with the several locations that you can model in the software at the arc flash study assessment. First of all, when you have included your arc flash module in your ElectricalOM software, you will see that some functionality will be enabled. For example, here you can see a module that is related to the arc flash, where we can see the calculations taken on and the arc flash, different arc flash calculations that have been considered. And also, when you're dealing, for example, in the circuit editor, we have here the options to perform arc flash study assessment. So these options will be enabled as soon as you add this add-on to your license. All right. Now let's go back and see the different locations that you can model in the system. First of all, in ElectricalOM, you can define the primary side of your low voltage transformer, the device used to protect the medium voltage panel, and we can perform arc flash assessment in this location. Then moving on, we can perform arc flash assessment on the low voltage side, and especially on the main low voltage panel, as we can see here. Next, we can define and perform arc flash study assessments on each protected device used in the network, like those two here. And of course, at the final load itself, so at this location, and of course, in each submain. Okay, so those are the locations that the designer can perform arc flash study assessments. Now, to show you how you can build something like that, I will create a quick new project and then quickly show you how you can model a similar diagram. First of all, we will insert the main supply, and by accessing the main supply, we will define a transformer. We will define the rating of the transformer, calculate the fault levels at the secondary of the transformer. And then when we're selecting transformers, we can see that the high voltage setting has been enabled to let us define high voltage settings. So here I will choose to use a high voltage protective device, where I will select a relay with electronic protection. Okay, so this is a new item that we have included in the latest version, where you can define the relay settings and also the CT parameters, and we support up to 4 curves. Selecting that now, we can choose to use the arc flash assessment here for the medium voltage panel. So by clicking here, we see that we are accessing the arc flash calculator for this specific location. So we are at the medium voltage panel. From here, we can see that we're using the IEEE standard to perform the calculations. We support the 2018 standard and also the older 2002 standard, but we recommend using the latest one. Now, in terms of the interface here, you can see that we have included all the necessary information for you to review and adjust to perform a comprehensive arc flash study calculation and inspect all the relevant parameters. Now, from the design, we need the voltage, of course, and the fault levels. And from that fault level, we will calculate the arcing current. Now, from the arcing current, we will calculate then the disconnection time, and based on all these parameters, we will end up calculating the incident energies. Okay, so we have two values here. Due to the latest standard, we can apply a correction which reduce a little bit the fault level, the arcing fault, to get to see if we can get a slower, let's say, disconnection time, which eventually might lead to a larger incident energy. And the worst case, of course, is the one that we will consider, and in this case is 9.34 calories per square centimeters, which will give us a category of PP3. Okay, now those details here are fully adjustable by the user. So we are providing all the necessary information for you to review. For example, in terms of the earthing electrode configuration, you can click on this information icon and review all the necessary parameters and what each setting is referring to. Now, if I choose to change the electrode configuration to VCB1, you see that the calculations are refreshed automatically, and we get a PP category of 2. A very important thing is that this diagram here that illustrates the boundaries, considering the restricted approach, the limited approach, the arc flash boundary, and the working distance are dynamically updated with any change in your parameters here. So for example, if I consider closer distance for this person to work on this equipment for this example, you see that the person will move closer to the incident of the arc flash, and of course, he's going to be exposed to a larger energy, leading to the assessment to consider a larger, PP category. Now, in terms of the results that we can give to our clients, to the end users, let's say, you can print reports, detailed reports from here, which will explain all the necessary parameters used, and of course, the warning labels that need to be considered for the maintenance. Also, we have included in our latest version a nice review of the different PP categories, where you can see which PP needs to be considered per category. And of course, we are also stating here that even if you get a 0 category, still you need to consider some minimal PP requirements. Okay, so all these details are derived from the NFP A70 standard. And of course, this is how we are performing an arc flash study assessment. As I said, now we are on the medium voltage panel. And let's see if I click OK and make a quick change to this device to the tripping here. And let's consider this to be, for example, 0.1. Go back to the arc flash study. We will see that the PP category now drops to 1. It was 3 before. And of course, the disconnection time during the arc fault has been set to 0.1. Okay, so we can see that there is a direct link between the settings of the device and, of course, the result of the incident energy to be considered. Now, I will OK this to accept all these changes, and then I will move on inserting my main panel. So I'm right-clicking to the source, insert switch port and 3-phase 1, and I will create a similar arrangement as we see here. So we have a bus bar connecting the main switch port, and at the incomer side we have an error circuit breaker at 2000 amps. So go back to this new project. I will access my main switch port, Okay, so let me call it main switchboard. And then on the protected devices, I will uncheck to use a device at the starting point, and I will use an in-camera device here, another current protective device, which I will change to an error circuit breaker. Okay, so I'll choose generic for this example. Okay, and then I will size my conductor. I will choose a bus bar, like in the previous show. I'll use 2,500, just 5 meters. And after applying this change, I can see that there is a problem with my selectivity study. And as Mike already mentioned, selectivity study, so a coordination and arc flash should be considered at the same time because the one might affect the other. Okay, so what I will do now, I will go here to the coordination. Okay, I will make some adjustments to this breaker. I mean, I'm just doing them to consider some settings that might be used later on. And then, of course, I will modify this relay so it will not overlap with my low voltage air circuit breaker. So I will increase a little bit the time here. I might choose another setting for the first curve. And I can see now that the selectivity study has been read out without any overlaps, so it's okay. Now, since we are in this environment of the selectivity study, we have I mean, after looking at the feedback from the users, we know that it makes sense to include the arc flash study assessment in this area as well. So in this case, we have included these extra options in the new version where you can quickly access your arc flash study assessment. So if I go to the arc flash study option here and then choose, I want to make a calculation on the panel, okay, we can see that the calculation is performed and we get a really dangerous case here. So we have exceeded the 40 calories per square centimeter, which is the limit. And in this case, we need to act and make some changes to make sure that we will avoid this case. Okay, so if I okay that now, the way to review it is by looking at the arc flash, the arcing current. Okay, so I enabled this option here. A new line will appear, as you can see from here, which is the arc fault, which is calculated at 22.3 kiloamps. Right, and as already Mike mentioned, in 90% of the cases, you can resolve these bad hazards by adjusting correctly the equipment. So what we will do here, we will adjust the instantaneous pickup of this equipment to be less than the arc fault here. So we will pick this option, this setting, and drag it to be on the left-hand side of this arc fault. Okay, now if we go back to our arc flash study and review what's going on, we see that we managed to get a PP of 0 because now the device is tripping instantaneously. So with some settings on the devices, we are able to achieve a more safe situation in terms of an arc flash incident. Now, of course, by adjusting this device, considering that we have downstream devices, we might affect the downstream coordination. So it's very, very important to include all the necessary parameters in place and perform all these adjustments to see what's the best case for us to consider. Now, if we go back to schematic and would like to show the calculations in terms of the arc flash assessment on our single line diagram, you can access the arc flash module here. If we navigate to the supply, we will be able to see the medium voltage panel as well. And by selecting those two options, we can click show where those details will appear directly on the single line diagram. So if I quickly include a submain here, okay, let me access that. Let me define a protected device here to be something like a fuse. Okay. Let me quickly define a cable, an installation method, the length of the run, and let me size the cable like that. Of course, we have some max ZS issues going on. I will not bother in this at this point, but I will consider going back to the selectivity study, where we can see that there might be some overlap here. So that's the case where we need to readjust the devices, of course, and maybe the upstream device as well. Okay. And now if we perform the arc flash study on the panel, we can see that we get the relevant PP category based on the device used to protect this panel, which is the BS88 fuse. Okay. Now, if we go back to the arc flash module, we can select this and choose to show. So we can include this PP category to this panel as well. Note that since I have modified my upstream equipment, the high voltage side equipment, I should go back to the supply, either from the selectivity study or from the supply editor, to make sure that there is any problem here derived. Okay, so this is how you perform arc flash study, how you build the network. And if I go back to the locations diagram I created here, I have an example here where this panel is protected by a specialized equipment by Eaton that has a specific component called ARMS. As Mike already mentioned, this is a special equipment that can be used on maintenance and of course can eliminate or protect us from any arc flash hazard during the maintenance. So if I access this panel and then go to the selectivity study and then enable the arc fault here, let me remove the other faults. So it's clear that we're dealing with the arc fault. Okay. If I select this Eaton device, you'll see that there is an RMS option here. So we can enable this RMS from here, and this will not override any selectivity done, but checks done, but it will be only considered for the arc flash assessment. So now if I access my arc flash, I see that this is disconnected instantaneously. And if I go to my reports, I will see that the RMS option has been used. So during this study, the designer has enabled the RMS option. And of course, in the label, we are putting there that if you're going to do maintenance, these figures here will be considered when you have the RMS maintenance mode enabled. Okay, so it's very, very important. Okay, so the RMS is enabled only when performing arc flash. Okay, and when you disable this option for the arc flash, you see it will go back to the selectivity, let's say, position. So the actual position when you're dealing with your selectivity and discrimination cable sizing. Now, other options that are important to demonstrate here are the case where we may have, for example, a motor here, where it's an industrial motor, and here we can consider the contribution to the short circuit capacity. So this will affect the fault levels, and as we've seen before, the fault levels are affecting the calculation of the arc flash incident energies. So it's very, very important to consider those options as well. Another case that is important to demonstrate is when we may have a backup generator in the system. So, or another source that is not the same as the essential, let's say, or the main supply. Now, in this example, which is the same example as before, we can see that the PP here is 4. But if we enable the generator, which eventually provides a smaller fault level, we can see that, and refresh the arc flash calculations from here, we can see that the PP has exceeded 4. Okay, so what this is telling us is that it's very important to consider the cases where the short circuit will change in the system. So if we have another source that can be operate in the system, it's good to make sure that we will investigate and evaluate all the cases here to make sure that we're going to address the worst case for the PP category. Okay, so in this case, we need to make sure that we will make the necessary adjustments for the equipment, turning on the arc flash option here. We can adjust, the device, and make sure that this will give us a better behavior in terms of the arc flash study assessment. Okay. Of course, now I've created some selectivity problems. So it's very, very important, as I said, to operate this function in combination with the selectivity assessments to make sure that we're not going to cause any other issues in the network. Okay. Of course, now I've changed that device, so I need to go and reevaluate my arc flash. Still is 3. So this is something which eventually helped after refreshing the calculations here. So we managed to drop the PP to 3 in this case, and of course, at the same time, we haven't affected any of the selectivity considerations for the downstream devices. So the other thing which is very, very important is when you have parallel source in the network. So transformers, for example, operating in parallel, this will affect your fault levels at the panels, and of course, eventually will affect the arc flash study results. So to make sure that you enable the parallel source operation, you can select the transformer in this case, and of course, the arrangement is supporting this functionality, like in this coupling arrangement. And then by going to the parallel source operation, you can check to use an identical source to parallel those transformers together. Okay. And of course, the calculations will be refreshed, and we can see here that the arc fault, which is less than usually is less than the normal fault level. You see that near here in this case is almost similar to the fault level of the source, meaning that there is a contribution from this source to this fault level here. Now I will show you how you can perform arc flash studies on an existing system, which is the common case. So as I said, we need to create a single line diagram, and then of course define all the necessary information like devices and cables, size, the equipment, so on. But you may have a case where you're inspecting an existing installation and you have been told to carry also arc flash study assessments for the panels in this network. So you may end up having something like that, which is a complete design. And then after navigating through the arc flash component here, you can choose a location. So the location is stated at the prefix of each description. So this is the panel, this is a protected device, this panel, so on. So usually you're going to perform an arc flash assessment on each panel. So I'm going to right click on that, select similar, and then select arc flash study location. Then what I will do, I will choose to use the arc flash study for each location. Okay, the software already performed the arc flash study for the selected locations, and then I will choose to show this on the network, on the schematic diagram. You can see that all these panels have been calculated and have been and next to them the relevant PP category has been considered. And at the end, what you like to do is to create a report. So by going to the reports, you can choose the reports you like to include. So we have included some arc flash specific reports. I have already defined a template for those. So I will use my cover page, of course, and the main supply. And of course, arc flash report here, analysis, PP category. Some selectivity study might be considered as well if you want. And of course, the schematic diagram. Okay, and then after doing this, it will create a complete report set with all this information included in a single PDF file. So now it's creating the selectivity study analysis with all the relevant curves. Okay, so we have the content page, as you know, main supply, and then we have the arc flash study overview with the analysis, for each arc flash study calculation. So we have also included this PP category table to explain each category and what PP should be considered for each category. And of course, selectivity studies with curves and the schematic diagram. So I think I've presented an overview of the tool that we provide here, which covers some cases that you might experience during your design and when studying the arc flash hazards. So I think that's concluding my presentation.
Excellent. Well, thank you very much, Dimitris. Hopefully that's been very useful for anyone who's using ElectricalOM there, or may already be using the Arc Flash or considering using the Arc Flash as part of their future work.